Welcome back. We are going to start talking about just in time or review number 7. We're going to convert and simplify using positive and negative exponents. I'm going to go back to the very, very beginning, not to make anybody feel uncomfortable or feel like I think you're stupid. You're not. But I want to make certain that everybody has the information that they're going to need. This piece is known as a base. And the exponent is a number that tells us how many times we multiply the base times itself. So if I have a value of 2 to the third, right? This is the same as saying 2 times 2 times 2, which is going to get me 8. All right? That's not going to be, it is not 2 times 3, which would be 6. All right, it's not that. I want to be sure that we're really clear on that. So, in fact, I'm going to go back and I'm going to erase this piece just because I don't want people to get confused. I don't want you thinking that that is a true statement, even though it says not. All right, so that's our base, right? 2 is our base in this case. Our exponent is a 3, and so it is 3 times that 2 multiplies itself. And I know that that's a bit of a mouthful, and I get that, but, you know, there's only so much I can do about it. Let's see here. Go with that, maybe. All right, so here I have a to the 0 power, which is equal to 1. And there's some really cool stuff that happens around that. If you ever want to know about it, let me know. Here I have the other thing that's super cool about having an exponent. If you have an exponent on a base, and that exponent is 1, the only thing you have there is you have that actual number. If I have a to the negative n, that negative exponent tells me it's living in the wrong part of the fraction. So if it's up in the numerator like this, I should have it, I could rewrite it as being 1 over a to the n, and we drop that negative as soon as it's in the right place in the fraction. And so we can say therefore, right? This is a fancy way of saying therefore, math language. So I have a to the negative n over b to the negative p is the same as saying my b to the p, right? I've moved this up and I've dropped off that negative sign. And here I have my a to the negative n that gets moved down so that it's a to the n. We drop off that negative sign and we're all set. We're done. We've rewritten it. All right, and I want to point out the one exception to this whole a to the 0 equals 1. It does not work when we're talking about 0 to the 0 power. 0 to the 0 power is not okay. It doesn't work because ultimately what we're trying to do is divide by 0, and that does not work. So we're not even gonna go there. So 0 to the 0 doesn't, for our purposes, does not exist. Okay, so here's an example. I have 7 to the 2nd power, or squared. I have 7 to the 5th, and I have 7. So I'm going to go ahead and I'm going to map these out. I do it just like, so I've got my 7 squared, there's my 7 to the 5th, and there's my 7. I'm just kind of reminding myself that that's actually 1. Sometimes people forget and they drop it, they don't actually count it. So then I wind up with 7 to the 8th power. So this is an example of the product rule, and I want to make real clear that this is the product rule, and here is the piece that's going to make it really different. There's also the power rule, which is different enough that you need to be really mindful of which one you're using. All right, so my product rule says a to the m power multiplied by a to the n power is the same as a to the m plus n power. So we are adding those exponents together. All right, we add them together. So it's like, there's my 2, there's my 5, there's my 1. I add those all together, and that's how I get to my 8. All right. Here I want to point out I've got 4 squared times 4 to the negative 5th. All right, so I could treat this like a power, or a product rule, In this case, excuse me, in this case I'm going to treat it like a, I'm going to treat it as a fraction or as a quotient. So let's go ahead and do that. So my 4 squared stays in the numerator. My 4 to the negative 5th becomes 4 to the 5th in the denominator. And now here's where this starts becoming helpful. I can go ahead and start canceling these guys out, and I wind up having 1, and I have the 4 3s, or the 3 4s still left in the denominator that I'm multiplying itself by. So I have 1 over 4 to the 3rd power, or 4 to the negative 3rd. All right, and so this is an example of the quotient rule, where if I have a the same base, keep in mind they have to be the same base, right? I have a value n and then I have a value p. I can treat that as a to the quantity of, and I'm going to put little parentheses around that, n minus p. And again, I've got to do my little spiel about a cannot equal 0 because otherwise we'd be dividing by 0. We're not allowed to do that. Okay, scroll down a little further, see what I can get done here, and then we will go, oops, here we go. So here I have 7 to the 1st power and over 8 to the 1st power, and then I'm going to raise it to the 0 power, and that's going to equal 1, and we're going to get to why that is in just a moment. But I want to point out, and maybe you'll spot it intuitively, but I want to point it out here intentionally. We've got 12 to the 3rd power, and I'm raising that to the 5th power. So I've got 12 times 12 times 12, and then I'm multiplying, that's my first one of the 12 to the 3rd. So here's my first one, there's my second one, here's my third one, my fourth one, and my 5th one. Now if I go through and I count them up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got 12 to the 15th power here. So here we're talking about a power rule, right? And this is where I wanted to make sure we're clear on the power versus the product. Here, I say my base raised to a power, and that whole thing is being raised to a power. We're going to say it's the same as that base where we multiply the two exponents. So m times n, right? So this is a little different, but very importantly different than our product rule. Okay, so our power rule, we're multiplying our product rule, we wind up adding them. All right, so here's an example. I have 5 over 11 to the 3rd power. I'm going to rewrite this as being 5 over 11 times 5 over 11 times 5 over 11. Well, now I can go ahead and multiply straight across, right? So that's what I do with fractions. I multiply the numerators and then I multiply the denominators. So I'm going to have 5 to the 3rd power and 11 to the 3rd power. So hopefully it's real evident why we can go from here to here, right? And this is known as raising a quotient to a power. All right, so if I have a over b to the m power, it's the same as saying a to the m over b to the m. And again, b can't equal 0 because then we'd be dividing by 0 and we're not allowed to do that. Okay. Here, again, we're going to talk about raising a product to a power. So we're going to take some multiple, right? Something we're multiplying, and then we're going to break it apart. All right, so here I'm going to have my exponent, right? Here I have the 2 to the negative 4 and 2 to the 4, right? And if you stop and think about it, that's exactly the same as saying I have 1 over, I'm sorry, I should have said negative 4 is up here. 1 over 2 to the 4 times x to the 4th, which when you think about it is the same. This and this are exactly the same. These are all the same, really. Here's another example. Maybe this one's a little clearer. I have a 7z that I've squared. So I have a 7z times a 7z. So and by my commutative properties, I can move these guys around. So now I've got the 7 next to the 7. Now we've got a 7 squared. I've got a z next to the z. So I have a z squared. All right. So that's an example of, they're both examples of raising a product to a power. Okay, so I'm going to stop here and I will resume with some more examples.